The universe does not like to be watched. It prefers the dark. It wraps itself in layers of radiation, dust, and unimaginable distance, hiding its secrets behind the veil of time itself. For most of human history, we have been staring into this abyss with one eye closed. We stood on the surface of our own pale blue world, looking up, trying to gauge the depth of the ocean by standing on a single shore. But depth requires perspective. To see the truth of a three-dimensional void, you need a second vantage point. You need to open a second eye. And for the first time in the history of our species, we have done exactly that. We blinked, and when we opened our eyes again, we were not just looking from Earth. We were looking from Mars. In October of the year 2017, something pierced the silence of our solar system. It was not a comet, though it moved like one. It was not an asteroid, though it looked like one. It was a traveler from the deep, an interstellar vagabond that had drifted through the void for hundreds of millions of years before stumbling into the light of our sun. We named it Oumuamua, the Scout. It arrived with a velocity that defied the gravitational mechanics of our local neighborhood, plunging toward the sun and then whipping around it, screaming back out toward the exit door of the solar system. It moved too fast to be captured. It moved too strangely to be understood. For years, the debate has raged in the halls of academia and the corridors of space agencies around the world. Was it a shard of a destroyed planet? Was it a hydrogen iceberg venting invisible gas? Or was it, as some dared to whisper, artificial? A derelict probe? A piece of technology drifting on the currents of the stars? The problem was not a lack of imagination. The problem was the math. When Oumuamua fled our system, it accelerated. It pushed itself away from the sun slightly faster than gravity alone would allow. It was a subtle deviation, a tiny push, but in the laws of celestial mechanics, a tiny push changes everything. It changes the origin. It changes the destination. It changes the identity of the object itself. We tried to track it. Every telescope on Earth turned its glass toward the retreating shadow. The Hubble Space Telescope strained its optics to the limit. But Oumuamua was small, dark, and tumbling. It was fading into the blackness at nearly 200,000 miles per hour. From our vantage point on Earth, the data began to blur. The error bars grew wider. The path became fuzzy. We were trying to calculate the trajectory of a bullet fired in the dark, based only on the sound of the gunshot. We lost it. The signal faded into the noise floor of the universe, and the visitor was gone, leaving us with a mystery that felt like it would never be solved. But we were wrong. We were not just watching from Earth. We had already extended our reach. While humanity argued on the surface of the third rock from the sun, silent sentinels were orbiting the fourth. We had machines circling Mars. The ExoMars Trace Gas Orbiter and the Mars Express, spacecraft designed to sniff the thin atmosphere of the red planet for signs of life, were perfectly positioned for something else entirely. They were millions of miles away from Earth. They offered a baseline, a massive gap in space that created a geometric opportunity we had never utilized for an interstellar object before. This is the power of parallax. If you hold your finger up against a distant mountain and close one eye, then the other, the finger seems to jump. That jump tells your brain how far away the finger is. It gives you depth. For decades, astronomers have used the orbit of Earth itself to create this parallax, waiting 6 months for our planet to move to the other side of the sun to get a different angle on the stars. But Oumuamua was moving too fast for that. We did not have 6 months. We barely had weeks. We needed a second eye, open at the exact same moment, but separated by an ocean of vacuum. We needed Mars. Astronomers have just revealed that they went back to the archives. They dug into the data streams recorded by those Martian orbiters during that critical window in 2017. They were looking for a ghost in the machine. And they found it. While Earth was blinded by the angle of the sun or the rotation of the object, the cameras on Mars had a clear line of sight. They saw the visitor. They tracked the intruder as it sliced through the emptiness. By combining the data from Earth with the data from Mars, they didn't just improve the calculation. they shattered the previous limits of precision. The accuracy of the trajectory has been improved by nearly tenfold. This is not a minor adjustment. This is the difference between knowing a car is on the highway and knowing exactly which lane it is in and how much pressure is on the gas pedal. The resulting path is the clearest, most precise orbital determination ever calculated for an object originating from outside our solar system. The blur is gone. The error bars have collapsed. We now have a razor-sharp line drawn through the history of the solar system, tracing the exact movement of Oumuamua as it defied our expectations. This breakthrough does something terrifying. It removes the ambiguity. When the data was fuzzy, we could hide behind the uncertainty. We could say that perhaps the acceleration was just a measurement error. We could say that maybe the telescope jitters accounted for the anomaly. But now, the jitters are gone. The path is locked. The acceleration was real. The non-gravitational movement was real. The object did, in fact, move as if something or someone was pushing it. But this story is not just about one rock. It is about a fundamental shift in how we exist in the cosmos. Until this moment, we were a single-point observer. We were a lonely species trapped on a lonely rock, staring out. Now, we are a multi-planet observatory. We have turned the solar system itself into a giant telescope. The distance between Earth and Mars is no longer a barrier, it is a lens. We have constructed an interferometer the size of the inner solar system, capable of catching the faintest whispers of movement from the interstellar dark. This changes the stakes for everything that follows. If we can track a small, dark, tumbling object with this level of precision using archived data from weather satellites orbiting another planet, what else can we see? What else has passed through our system that we missed because we were only looking from Earth? The void is full of wandering stones and dead stars. But it is also full of silence. And in that silence, things are moving. Things that do not belong to our sun. The improvement in the trajectory data forces us to re-examine the origin of Oumuamua. With the old data, the backtracking led to a broad region of the sky, a chaotic mess of potential home stars. It was a needle in a haystack of infinite size. But with the new Martian data, the haystack has been burned away. The path points backward with unnerving accuracy. It points to a specific corridor of the galaxy. It points to a specific time. And it forces us to confront the reality that this object did not just wander here by chance. The mathematics of its arrival, now purified by the Martian observations, suggests a needle-threading event that becomes statistically uncomfortable to accept as a mere accident. We often talk about the search for extraterrestrial intelligence as a search for radio signals, for beeps and squeaks in the static. We listen for a phone call. But what if the message isn't a sound? What if the message is a trajectory? What if the geometry of the path itself is the signal? To see it, you need to be smart enough to look from two planets at once. You need to have mastered spaceflight. You need to have synchronized your clocks across light minutes of distance. Perhaps Oumuamua was not just passing through. Perhaps it was a test. A test to see if the civilization in this system had opened its second eye yet. And if it was a test, the results have just come in. We passed. We saw it. But we saw it years too late. The object is gone, racing into the dark at a speed we can never catch. But the data remains. The ghost left footprints, and for the first time, we have the forensic tools to analyze them properly. The implications of this new clarity are profound. It means that the next time, and there will be a next time, we will be ready. We will not just watch from Mauna Kea or the Atacama Desert. We will watch from the Jezero crater. We will watch from the orbit of Jupiter. We are building a fence around our star, a tripwire made of sensors and mathematics, designed to catch the shadows that slip between the worlds. The refining of Oumuamua's path also revitalizes the most controversial theory of them all. If the object was a nitrogen iceberg, as some claimed, the outgassing required to produce the observed acceleration would have significantly altered its mass and its rotation. With the new precision from Mars, we can check the mass constraints again. The natural explanations have to fit into a much tighter box now. there is less room for error. There is less room for excuses. If the natural theories cannot squeeze into this new, narrow tunnel of reality defined by the Mars data, then we are left with the impossible. And as Sherlock Holmes once said, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. We are standing on the precipice of a new era of interstellar science. We are no longer guessing. We are measuring. The chaos of the void is being brought to order by the triangulation of our machines. But order brings its own fears. When you turn on the lights in a dark room, you see everything. You see the furniture. You see the dust. But you also see what has been standing in the corner, watching you sleep. Mars has handed us a flashlight. We have pointed it into the dark. And the beam has illuminated a path that leads out of our solar system into the deep unknown, pointing directly back at the place where the monsters live. But to find them, you cannot simply look where the shadow is. You must look where the shadow is going, and more importantly, how it is moving. This is where the story of Oumuamua shifts from a tale of observation to a mystery of physics. When we say the trajectory accuracy was improved tenfold, it is easy to let that number slip by as a mere statistic. In the world of high-stakes astrophysics, however, an order of magnitude is everything. It is the difference between a blurry photograph of a face in a crowd and a high-definition scan of a retina. The previous calculations, tethered to the Earth, left us with a cone of uncertainty that spanned millions of kilometers as the object retreated. We knew it was leaving, but we could not say with absolute certainty how hard it was being pushed. The data from Mars changed the texture of reality. By locking down the position of the object from a second vector, we effectively pinned the butterfly to the corkboard. We stopped the trembling of the data. And when the trembling stopped, the anomaly remained. This is the crucial detail that keeps astronomers awake at night. Usually, when you get better data, the anomalies disappear. The ghosts turn out to be glitches. The mysterious signals turn out to be microwave ovens in the break room. Precision usually kills the mystery. But in the case of Oumuamua, precision made the mystery invincible. The clearer the path became, the more impossible the movement appeared. The central problem is something called non-gravitational acceleration. In the vacuum of space, an object should surrender entirely to the curvature of spacetime. It should slide down the gravity well of the sun and climb back out, trading kinetic energy for potential energy in a perfect, predictable exchange. It is a dance governed by Isaac Newton and Albert Einstein, and the steps never change. But Oumuamua refused to dance. As it moved away from the sun, it slowed down, as all objects must. But it did not slow down enough. It retained a tiny fraction of speed that it should have lost. It was behaving as if it had an engine. Not a warp drive or a chemical rocket, but a subtle, persistent force pushing it from behind, fighting against the gravity of our star. Before the Mars data, we could argue about the magnitude of this push. We could suggest that perhaps our measurements of the object's position were slightly off due to the wobble of the Earth or the atmospheric distortion of our telescopes. But the Mars Express and the ExoMars Trace Gas Orbiter do not suffer from atmospheric distortion. They float in the hard vacuum. Their view is crystal clear. And their data confirms that the push was real. The object was being propelled. This leaves us with two possibilities, and both of them are uncomfortable. The first is that Oumuamua was a comet. Comets heat up near the sun. The ice on their surface turns to gas, exploding outward in jets. These jets act like thrusters, pushing the rock in the opposite direction. It is a natural engine. But if Oumuamua was a comet, it was a ghost of one. It had no tail. It had no coma. It had no cloud of dust surrounding it. Deep observations looked for carbon-based molecules, for water, for anything that indicates a comet. They found nothing. It was a dead stone. If it was a comet, it was made of something we have never seen before. Some theorists proposed it was a hydrogen iceberg, a chunk of frozen hydrogen that would turn to invisible gas, leaving no trace. Others suggested nitrogen ice, a shard from a Pluto-like planet in a distant system. These theories are elegant. They try to force the anomaly back into the box of the natural world. But the Mars data tightens the noose around these explanations. If the object was venting gas, that gas would exert torque. It would spin the object. Oumuamua was tumbling, yes, but its rotation was chaotic and complex. The new trajectory constraints force us to ask if the venting required to produce the acceleration matches the spin we observed. The puzzle pieces do not fit cleanly. You have to hammer them into place. The second possibility is the one that science tries to avoid until the very end. The possibility that the push was not internal, but external. Solar radiation pressure. Light itself carries momentum. When sunlight hits a surface, it pushes it. For a rock, this push is negligible. It is like throwing a ping-pong ball at a freight train. But if the object is not a rock, if it is incredibly thin, incredibly light, and incredibly reflective, the sunlight becomes a wind. And the object becomes a sail. The refined path calculated from the Martian orbit fits the solar sail hypothesis disturbingly well. An artificial object, designed to harness the radiation of stars, would move exactly the way Oumuamua moved. It would accelerate away from the sun, pushed by the photon stream, without leaving a trail of gas. It would tumble if the sail was damaged or uncontrolled. The tenfold accuracy of the new data does not rule this out. In fact, it sharpens the argument. It confirms that the force acting on the object followed an inverse square law relative to the sun, exactly how light pressure works. But why would a sail be here? Why would a piece of alien technology drift through our back garden? The new trajectory analysis suggests it wasn't targeting us. It wasn't slowing down to say hello. It was drifting. This paints a picture of the galaxy that is far more haunting than an invasion fleet. It suggests a galaxy filled with wreckage. If Oumuamua was artificial, it was likely space junk. A discard. A buoy cut loose from its anchor. A piece of a Dyson swarm that shattered a billion years ago. We are not being visited. We are stumbling upon the trash of civilizations that may have died before the Earth was born. The ExoMars TGO was designed to look for methane on Mars, to hunt for the biological signatures of microbial life in the red dust. It is ironic that its most significant contribution might be tracking a technological signature from another star. The spacecraft was looking down, but its data forced us to look up. It proved that in the game of interstellar detection, parallax is king. We cannot understand the three-dimensional universe from a two-dimensional mindset. This new level of precision also reveals the terrifying speed of the object relative to the local standard of rest. Oumuamua was sitting still. That is the true anomaly. Before it entered our solar system, it was practically stationary relative to the average motion of the stars in our neighborhood. We were the ones who hit it. Our solar system, orbiting the galactic core at incredible speed, slammed into this object like a windshield hitting a bug. It was waiting. It was parking. And this specific kinematic characteristic, being at rest in the galactic frame, is extremely rare for natural objects. Stars move. Comets move. Asteroids move. Very few things just sit there in the dark, waiting for a star system to pass by. The Mars data solidifies this rest state calculation. It confirms that Oumuamua was not just a random rock thrown from a chaotic explosion. If it was ejected from a planetary system, it was ejected in a way that perfectly cancelled out the motion of its parent star, leaving it motionless in the galactic stream. That requires a very specific, very unlikely set of gravitational kicks. Or, it requires intent. It requires a navigation system that brings the vessel to a halt, to float in the quiet waters between the stars, perhaps to listen, perhaps to recharge, or perhaps because it died there. We are now in possession of a flight plan for a ghost. We know exactly where it entered, and thanks to Mars, we know exactly where it left. The exit vector is particularly interesting. It is heading toward the constellation Pegasus. It is diving back into the deep dark, away from the warmth of any nearby stars. The precision of the new plot allows us to project its position thousands of years into the future. We know where it will be when humanity is dust. We know where it will be when the sun expands to swallow the Earth. It will still be drifting, a silent testament to the fact that we were not alone, even if we never met the makers. The use of Martian satellites to track interstellar objects has opened a new door in astronomy. It has proven that we can utilize our existing infrastructure in ways the engineers never imagined. We have turned our planetary probes into a deep space sensor network. But this success brings a hunger for more. If we had seen Oumuamua sooner, if we had triangulated it with Mars on the inbound leg rather than the outbound leg, could we have intercepted it? The math says yes. If we had this level of precision earlier, we could have launched a chaser. We could have caught the visitor. We could have touched it. But we were slow. We were blind. We were arguing about what it was while it was already saying goodbye. The tenfold accuracy is a triumph of data analysis, but it is also a monument to a missed opportunity. It is a receipt for a package we failed to open. And now, as the data settles and the papers are published, a new question arises. The clarity of the path allows us to look backward with renewed confidence. We can trace the line not just through our solar system, but back out into the void from whence it came. We can rewind the clock millions of years. And when we do, the line points to a region of space that is unsettlingly empty. It does not point clearly to a nearby star system. It points to the void. It points to the darkness between the spiral arms. It suggests that Oumuamua has been traveling for a very, very long time. It suggests that it is a traveler from the deep history of the Milky Way. And this brings us to the most disturbing realization of all. If the galaxy is old, and if civilizations rise and fall, then the space between the stars should be littered with their remains. Oumuamua is likely not the first intruder to pass through our system. It is simply the first one we saw. It is the first one we tracked with the open eyes of 2 planets. How many others have skimmed the atmosphere of Earth while we were sleeping? How many others have crashed into Jupiter, vanishing into the gas clouds without a whisper? The universe is not empty. It is full of things that do not want to be found. And now that we know how to look, now that we know how to use Mars as a second eye, we are going to find them. But are we ready for what comes next? Are we ready to find something that isn't just a dead rock or a broken sail? Are we ready to find something that changes its course not because of sunlight, but because it sees us watching? It forces us to confront the possibility that the universe is not a passive backdrop, but an active ecosystem where we are merely the newest biological curiosity to crawl out of the ocean and look at the sky. The realization that Oumuamua's trajectory was influenced by non-gravitational forces does not just rewrite a textbook, it rewrites our place in the food chain. If it was a machine, even a broken one, it implies a level of industrial capacity that dwarfs our own. We struggle to send tin cans to Mars. Someone else, somewhere in the deep past, may have been broadcasting seeds across the spiral arms of the galaxy like a dandelion scattering its spores in the wind. The improved data from the Martian satellites has effectively armed us for the future. It has validated a new methodology. We are no longer limited to the blurry, trembling view from Earth. We now know that by combining data from different worlds, we can achieve an accuracy that borders on the miraculous. This is the prelude to a new kind of defense. The upcoming Vera Rubin Observatory in Chile, set to open its massive eye soon, will not just look at the stars, it will watch the space between them. It is expected to find not one Oumuamua, but hundreds. Perhaps thousands. We are about to discover that our solar system is not a lonely island, but a busy intersection in a galactic metropolis, filled with the traffic of drifting stones and silent probes. But there is a melancholy to this discovery. We now have the math to prove exactly where Oumuamua went, but we lack the speed to follow it. Several mission concepts, like Project Lyra, have been proposed to chase the visitor down. They involve slinging a spacecraft around Jupiter, then diving into the Sun to perform a Oberth maneuver, firing engines at the point of maximum velocity to gain enough speed to catch the fleeing object. It is a desperate, beautiful plan, a Hail Mary pass into the void. But even if we launched it today, it would take decades to catch up. By the time we arrived, the probe would be old, and the people who built it would be dead. We are chasing a ghost with a butterfly net. The tragedy of Oumuamua is not that we don't know what it is. The tragedy is that we saw it too late. It was the Rosetta Stone of interstellar astronomy, a package delivered to our doorstep containing the answers to questions we hadn't even thought to ask, and we let it slip through our fingers because we weren't looking from the right angle. The lesson from Mars is clear: never blink. The universe moves fast. The anomalies do not wait for peer review. They appear, they shatter our paradigms, and they vanish. This brings us to the ultimate question of scale. Oumuamua was small, perhaps only a few hundred meters long. It was hard to see. But if the galaxy is truly ancient, and if technological civilizations have risen and fallen over billions of years, there should be things out there that are not small. There should be artifacts that do not drift like stones, but loom like monuments. There should be footprints in the galaxy that are impossible to miss. We look for radio signals, but signals fade. We look for laser flashes, but lights go out. Physical structure, however, endures. If a civilization reaches the level of a Type 2 or Type 3 on the Kardashev scale, they do not just build probes, they rearrange the stars themselves. They harvest the energy of entire systems. They leave behind not just debris, but emptiness. The trajectory of Oumuamua points back into the dark, towards a history we cannot read. But if we turn our gaze from the single, small object to the larger structure of the cosmos, we see patches of the sky that are disturbing for a different reason. We see places where the stars seem to have gone missing. We see vast regions of cold emptiness that defy the standard models of cosmic evolution. Oumuamua was a presence where there should have been nothing. But there are places in the universe where there is nothing where there should be something. We call these places voids. They are the deserts of the universe, spherical bubbles of nothingness millions of light-years across. Most of them can be explained by the expansion of the universe and the flow of dark matter. But there is one void that stands apart. A void so large, so empty, and so anomalous that it chills the blood of the astrophysicists who study it. It is not just a gap in the map, it is a hole in reality. If Oumuamua was a scout, perhaps it came from a place where the work was already finished. Perhaps it is a survivor from a region of space that was harvested, consumed, and left dark by a hunger we cannot comprehend. The precision we gained from Mars tells us where the rock is going. But to understand where it might have come from and what kind of civilization could build a solar sail that survives millions of years, we must look at the macro-scale evidence of advanced life. We must look at the possibility that entire galaxies can disappear. We must look into the Boötes Void. This is a region of space where thousands of galaxies should exist, but only a handful remain. It is a perfect sphere of darkness in a sea of light. Is it a natural anomaly, or is it the aftermath of a Type 3 civilization expanding its territory? If Oumuamua was a technological breadcrumb, the Boötes Void might be the bakery that burned down. To understand the true potential of the intelligence that might have built our visitor, we have to look at what happens when a civilization doesn't just launch a probe, but consumes a sector of the universe. We explore this terrifying possibility, the idea that the universe is full of holes because someone is eating the stars, in our deep dive into the great nothing. If you want to see the scale of what might be out there, look at the evidence in the Boötes Void. Is this proof of a Type 3 civilization? It is the other half of the puzzle. One is a whisper, the other is a scream. Until next time, keep looking up.